All right, so let's have a look at how this one's going to work. Okay, so we still have an object that is rolling horizontally off of a table. Table, cliff, doesn't matter. Okay, it's rolling off horizontally. Okay, but we don't know how fast it's going. When it does that, we just know it's horizontal, right? Since we know that it's horizontal, we know the initial vertical velocity is 0. Because it doesn't say it was thrown off, it says it rolls off. Okay, it's the same as falling or being dropped. Okay, we know that the vertical distance is the height of the table, so that's 1.2 meters. Okay, and we know the acceleration is 9.81 meters per second squared. So that's what we know vertically. Horizontally, all we know is how far the ball travels before it hits the ground in a horizontal direction, and that's 0.85 meters. Right, but we're being asked to calculate the horizontal velocity or horizontal speed. Okay, that means I need time. I'm obviously not getting it from my horizontal information. So I've got to look to my vertical information to get it. Okay, I have VI, I have D, and I have A, which means, again, it's back to this formula. We've used it every single time we've had a question like this. That has been the go-to formula for this. All right, VI is 0, so that's gone. We're solving for T. Okay, so I'm going to divide both sides by half of A and then square root. So that's going to be 1.2 divided by 1/2 times 9.81, all square rooted to get me the time. Okay, so we're looking at 0.49 seconds. Okay, is our flight time or falling time. Right, now that I have that, I'm just going to plug it in over here, okay, in order to calculate V, because V equals D over T, 0.85 over 0.49, right, will tell us the speed it rolls off at. Okay, so we'll have our 0.85 divided by that number. So it rolls off the table at 1.7 meters per second. All right, so now you've seen kind of one of each, okay, of the types of questions that you could get for rolled off horizontally type questions. Okay. All right, any questions or concerns about that one? Now, yesterday we looked at, or we watched the Mythbusters bust the Mega Whoosh projectile thing, right? Today we're going to look mostly at now angled projectiles. So anything that's fired, shot, or in some other way projected at an angle above the horizontal, right? Those ones are going to travel farther because they have an initial vertical velocity that is upwards, unlike throwing something horizontally, which has no vertical component initially. Okay, so these ones will go further and they'll look a little bit different. Now, one of the places where we saw that already was obviously the Mega Whoosh. We also saw it with the ridiculous jump in the Speed movie. Okay, but before CG, the only way to make a cool looking car jump in the movies was to actually perform a cool looking car jump and film it from different angles. All right, the show that best did this was the Dukes of Hazzard, not the movie, because that movie was an absolute travesty. Okay, it was shameful, it was terrible. Okay, Willie Nelson is not Uncle Jesse, sorry. Okay, but the original show was actually quite wholesome. It was actually quite a wholesome show, but it's not being aired anymore on television because there's a Confederate flag on the top of the car, and that offends people. So it's not. You can't even watch it on TV, unfortunately, anymore. Yes, actually, you can't even buy the replica cars anymore. Okay, because they have that symbol on them. Okay. And I mean, rightfully so. That symbol did represent some awful things. I get that. But I mean, it was a wholesome show. Like, come on, really. That's the worst thing out there. But whatever. Okay. So what we're going to look at here is kind of what do you have to go through if you're going to film one of these jumps? Because you want it to look right. Okay. And you want it to be, to be convincing. So when they were going to do one of these jumps, they would have a bunch of calculations to do. First off, they'd have to know how far horizontally they wanted the car to go. Okay, because they had to, clear a creek bed, or they had to clear a barn. You wouldn't believe some of the stuff they jumped this car over. Okay. Now, the really tragic part of the really cool looking jumps on television is that every time they performed one, a beautiful 69 Charger died. Okay. Yeah. 69 Charger, I mean, that's just a beautiful car. It's one of the best designed cars ever. Okay, but one died every single time. In fact, they destroyed like well over 300 of these things during the filming of that show. Okay, in fact, by the end of its run, they couldn't find 69 Chargers to wreck anymore. They were actually filming Challengers from different angles because some of their body work was similar, and you could buy it. Anyway, so they would do these calculations, and then they would drive the car. And there was actually a driver in these cars. Okay, not like, you know, today they'd have done it by remote control or by CG or whatever. Okay, there actually had to be a person behind the wheel each time they jumped the car. Imagine being that guy. All right. Now you can always tell a stunt driver, okay, because their thumbs are a mess. They break them all the time. Okay, when you're a stunt driver and you're going to do a jump, you hold the steering wheel like this with your thumb on the top. If you grip it like we normally do with your thumb around it, you will snap your thumbs off when you land. Each and every time, snap. Okay, so they actually grip it like this. But okay, it had to be performed that way, and they had to calculate the angle they were going to jump from, because they would have to build a ramp, and they would have to calculate the speed at which they were going to run the car up. They weren't just going to go, okay, build a ramp and drive at it as fast as you can. Okay, because then it might not look right. And you're going to see, because I'm going to show you here, there's actually a YouTube video that has every jump ever. I'm not going to show you the whole thing because it's like 12 minutes long. Okay, but every jump ever in the show, The Dukes of Hazzard. Right? Some of them don't go quite according to plan. Right? The whole idea of making this look convincing is that you just cut away at the right time. Okay? Like you'll see the car coming in and they just cut away and the car's driving away completely fine, when in fact the car was completely destroyed. Okay? But you don't see that part. Sometimes though, they don't get the editing quite right, and you can actually see the car destroy itself. And then suddenly this other car, okay, the one that never gets jumped, drives away looking shiny and clean, whatever. Okay? So we're going to have a look at that, but they do have to do similar calculations to what we're going to be doing, okay, when we talk about projectile motion. So after watching the General Lee jump a whole bunch of times, which never gets old, I mean, you just never get tired of watching that. So we have the General Lee jumping the riverbed. The following information is known. The speed of the General Lee is 32 meters per second when it leaves the ramp. Okay, the ramp is angled at 20 degrees. Okay, we are looking for the distance across the river and the maximum height the General Lee reaches. All right, so this is what we're going to assume. Okay, we're going to assume that the launch point and the landing point are at the same altitude. Okay, there's no change in height from one side to the other. Okay, we're going to assume that the General Lee launches itself at a 20-degree angle at 32 meters per second, okay, which is like over 120 kilometers an hour. The General Lee, as we saw in the video, follows a projectile arc like anything else would until it encounters the ground on the other side of the river. So what we want to calculate is how far horizontally is it going to travel, and what is its maximum height above the riverbed. Okay, so with all projectile motion questions, the first thing we want to do is break it down into the horizontal component, which is still an object traveling at a constant speed, and the vertical component, which is undergoing accelerated motion. All right, so we're going to split it up into vertical and horizontal parts. Okay, initially, here's what we know. The acceleration of the General Lee is negative 9.81 meters per second squared. The rest of the stuff I'm going to have to calculate. So we know that when it leaves the ramp, it's moving at a velocity of 32 meters per second directed 20 degrees above the horizontal. So this is a vector. This is my velocity vector or my projected vector. That vector has a horizontal component. And since this is a velocity vector, this horizontal component is going to be my constant horizontal velocity that the General Lee will travel at throughout its entire flight. Okay, so calculating this side of the triangle, okay, will give me my horizontal velocity. Similarly, this velocity vector has a vertical component. And since this is only true at the instant the General Lee leaves the ramp, this vertical part represents my initial vertical velocity, because that's going to change due to gravity. Okay, how do I calculate those two components? Like if I want to find VI, how do I calculate it? No? Right, sine of 20 times 32. I'm finding the vertical component of this vector. Okay, all I'm doing is breaking this thing down into its horizontal and vertical components. All right, so VI is going to be the sine of 20 times 32 meters per second. Okay, so this thing is initially moving at 10.94 meters per second. Obviously, I'll keep all those decimal places in my calculator. Meters per second, and that's up. Okay, it's moving at 10.94 meters per second up. I want to do the same thing now with my horizontal information. I want to find the horizontal component. That's going to be the constant horizontal velocity throughout the entire flight. Okay, that's going to be cos of 20 times 32. All right, so horizontally, the General Lee is moving at 30.07 meters per second. Okay, so I've calculated a fair amount of stuff here, but I still don't have that much information. The rest of the information has to come from me analyzing the context. Okay, so from a vertical perspective, when the General Lee flies off the ramp and then comes back over here to the same height, how fast is it going vertically here? Right, the same speed it was launched at vertically. Okay, remember, what goes up must come down. If I'm only watching the General Lee from a vertical dimension, all I see is the General Lee go up and come back down. Okay, since it goes up and down the same distance at the same rate of acceleration, it has to come back to the ground at the same speed it left at. All right, that's just one of those things that we have to remember. Okay, those two speeds are always going to be equal. So VF, as long as the altitude is always the same, which for us it's going to be, okay, 10.94 meters per second, but now it's negative. Okay, so no different than if I threw an object up in the air. Okay, it's exactly the same thing. Like straight up in the air. I mean, straight up in the air. All right, I have A, I have VI, and now I have VF. What can I calculate? Time. Is that something we were always looking for? Yeah, because it's the one thing that horizontal and vertical components share. So that's what I want to calculate next. I'm going to use A equals VF minus VI over T. Okay, I'm just going to manipulate it for T. So T will equal negative 10.94 minus 10.94 divided by negative 9.81. Whoa, I missed the decimal. Again, 10.944644. Okay, so I've got 2.23 seconds here is my time. Right? So the General Lee was in the air for a long time. Right? I mean, that clip took a while. I mean, yes, they slow mode part of it, but still, okay? Oh, it'll mess it up. Okay, if I don't put this negative here, I get 0.
No, but like if all of the numbers are positive, then you just add the 2 tens and then divide by 9.81.
Well, I added the 2 tens because negative 10.94 minus 10.94 is 2 times, right? Like I know I shortcut on the calculator, okay? But that's because, yes, you're right. I made everything positive, sort of, okay? I didn't really, but
Just to make it easier on the calculator instead of having to write it all.
yes. You could just multiply this number by 2 and divide by 9.81, but I shouldn't have shortcutted. I just forced a habit that I did that. Realistically, I should have done it like this: negative 10 minus 10 over negative 9.81. Okay, I just knew it would come out to the same answer when I did it. Okay, so we've got a time of 2.23 seconds, which now I can move over here because I know they share the time. Can I calculate how far it is across the riverbed? Yeah, V equals D over T. Okay, so to calculate distance, it's V times T. So I take that 2.23, sorry, with all the decimals. And I multiply that by my horizontal velocity, 30.07016,387. All right, it's 67 meters across the riverbed. That's considerable. That's a long way to fly a car. All right, so any one part of that mathematically difficult? No, we know how to calculate vector components. We know how to do acceleration problems. We know how to do V equals D over T problems. Okay, that's all we're doing here. Okay, is vector components, acceleration, and V equals D over T. Nothing difficult. All right, so that's the first part of this question, was calculating how far the general E flies across the riverbed. The second part of the question was, what's the maximum height of the general E? Okay, it says here, how high does it, above the ground is it? All right, so we're looking for its maximum vertical displacement. Now, according to that diagram, where does that happen? Middle of the arc. Okay, so there's two ways to do this. I could divide the time in half, go with my VI, because it would still be true, okay, and solve for the vertical displacement using this. Okay, I could say that D equals VI times T plus 1/2 AT squared, and just use half of that 2.23 because that's where that's supposed to happen, is halfway through. Everyone okay with that? I find people screw that up all the time. I don't know why. Okay, well, actually I do know why. Most of the time they forget to divide the time by 2. Okay, and then they get this ridiculously large number. Okay, but here's the other way we can do it, and I find people do this better. Okay, how fast vertically is the general E going at its maximum height? And remember, all I'm seeing if I'm only watching the vertical motion of the general E is this. I see it go up and come back down. How fast is it going at its maximum height? 0. Okay. If I remember that at the maximum height, any object moving vertically has a velocity of 0 because that's the turnaround point, I can solve this using this formula. And I find people screw it up less. Okay. You can do it whichever way you want, but I find people screw this way up a lot less often. All right. So I'm going to make VF 0. I've already got VI because I calculated it was 10.94. I know the acceleration, and I'm looking for the vertical displacement at this point, okay, when VF is 0. Okay, so if I manipulate, I'm going to have D equals VF squared minus VI squared over 2A. So for this one, that's going to be 0 squared minus 10.94 squared divided by 2 times negative 9.81. Okay, so when I do that, I find that the maximum height of the generally is 6.1 meters. Okay, that's about 20 feet. Right, like dropping a car off the top of the gym. Except that you're not dropping it, you've already jumped it and it's moving really fast. Okay, so there's, yeah. Okay, so 6.1 meters is my maximum height for that one. Okay. But really, all it breaks down to is understanding the context and being able to do an acceleration problem. Okay, that's all we did there, was use one of our acceleration formulas. Okay, now if I did this the other way, right? The other way I was telling you, you could use this, d equals vi times t plus 1/2 at squared. I should get the same answer. Okay, I should get the same answer. Right, I would just go 10.944644459 times I'm just going to go 1 point. I'm going to round here because I didn't do this very well. 1.115. Okay, I get the same answer. Right. You can do it either way. Either way will work. It's just an acceleration problem. You've got a set amount of information. You can do it however you want. Okay, just I find, like I say, that most people screw that one up by forgetting to divide the time by 2. Okay, or they forget to put a square in there or something silly. Okay. All right, making sense? Last semester, that was the unit exam question for projectile motion. Okay. Had to calculate the horizontal distance and the maximum height. Because it's changing direction, right? It starts initially going upwards, but the acceleration is going to change direction as it comes down. So I have to show that the acceleration is slowing it. If I make that positive, then it's going to say it goes faster as it goes up, and the distance, the height's going to be ridiculous, right? With me there? Okay. I have to reflect that the acceleration is down and it was initially moving up. Okay, everybody all right with how that one worked? Okay. Try this one. Okay, so I have a cannonball this time. It's fired at a 40-degree angle at a speed of 140 meters per second. I want the same two things you did just a minute ago for the generally. Okay, so looking at this one here, okay, here's how it starts out. We got the cannonball fired at a 40-degree angle. And I know this doesn't look like a 40-degree angle, but that's fine. Okay, so 40-degree angle at 140 meters per second. So it's just like the general E question. There's nothing different here. Okay. So we are looking for how far it travels as well as the maximum height. So again, we want to break this up into its vertical and horizontal components. So this side here of this vector, okay, is the horizontal component of the 140 meters per second. It is the constant horizontal velocity the cannonball will travel at as it travels through the air. Okay. Then we have this side here, which is the initial vertical velocity, which will only be that value at the initial instant, and then it's going to change due to gravity, right? But this will be VI vertical. All right, so VI vertical, we will calculate by going sine of 40 times 140 meters per second. Okay, so we got 89.99 meters per second up. All right, so that's positive. We also know the acceleration is negative 9.81 meters per second squared. And what's VF if we're talking about the whole trip? Right, negative 89.99. Right, that's just one of those things we have to remember. Those two velocities have the same magnitude, but opposite direction. Okay, horizontally speaking, our horizontal velocity, okay, is going to be the cos of 40 times 140. All right, so 107.246 meters per second, and that number's not going to change. Okay, if I want to calculate the horizontal velocity, what else do I need? I'm sorry, the horizontal distance, sorry. What else do I need? Time.
Sorry for the interruption, but could everyone please head over to the church for the service?
Okay. Yeah, we'll finish it real quick here. Okay, so guys, when we go over there, all right, so with our time here, okay, we calculate the time using our vertical information, right? So that's just going to be T equals VF minus VI over A. We bring the time over here and use it to calculate D, okay, and then we'll do the vertical height another time, right? But same thing we did with the general E question. Okay, so for this one, okay, we start out with, okay, that we have a 40-degree launching angle. Okay, we know that it's going to do this and follow that arc. Okay, so 40 degrees at 140 meters per second. Okay, we want to break this up into our vertical and horizontal components. Okay, we know that acceleration vertically is negative 9.81 meters per second squared. That's all we know right now. Okay, the rest of it we have to calculate. All right, so as we did before, because this is a velocity vector, the vertical component of it, or the y component of it, will represent our initial vertical velocity, sine of 40 times 140. Okay, so 89.99 meters per second is our initial, and that's positive. Okay, and our horizontal one is the x component of that velocity vector. Okay, so v horizontal, okay, is going to be the cos of 40 times 140. Okay, so 107.246 meters per second. And remember that that velocity is not going to change because horizontally the object travels at a constant velocity. Okay, it doesn't accelerate. All right, if I am dealing with the entire flight and I want to calculate this distance here, horizontal, right? What do I need to know about the speed, the vertical velocity, sorry, of the object when it hits the ground over on the other side? Well, I'm going to need time, but I need the vertical velocity final first. What do I need to know about that? It's the same as my initial unless I'm told otherwise. Okay, so you assume that the takeoff point and the landing point are the same elevation unless it specifically tells you otherwise. If it does, then there's an extra calculation that goes in there. Okay, we won't get to that yet. So for right now, okay, that's what we have to do. We have to calculate what VF is, or not calculate it, but actually just write it down. Okay, and that VF is negative 89.99 meters per second. All right, what can I calculate now? Time. All right, so to calculate time, I'm going to go negative 89.99 minus 89.99 divided by 9.81. In other words, VF minus VI over A, right? Okay, so once I have the time, whoop. All right, so the flight time is 18 seconds. Well, 18.35 seconds. Okay, so that's our flight time. That also applies to the horizontal part. Okay, can I calculate the horizontal distance with speed and time? Okay, so V times T, take my 107.246 All right, this thing travels almost 2 kilometers. In fact, to the correct number of significant figures, it does travel 2 kilometers. Okay, it'd be 2.0 times 10 to the 3 meters. Absolutely, totally, for a cannonball, totally realistic. Okay, especially at that angle. All right, artillery shells, okay, modern day cannonballs, they're fired oftentimes 50 to 100 kilometers. Okay, yeah, okay, you just have to impart enough speed and the right angle. Okay, so more powder, bigger angle, okay, and you can make them go pretty much anywhere you want. All right, anybody got any questions on that one? Everyone's good with that? Okay. The next thing we were supposed to do is calculate the maximum height of the cannonball. All right, so again, there's 2 ways to do that. We have to remember that maximum height occurs here. Okay, we're looking for the vertical displacement at the halfway point of the flight, where we're either using half the time or we're using that VF is 0, one or the other. Okay, if I'm using half the time, then I'm going to go V I times T plus 1/2 AT squared. So that'll be 89.99 times 18.35 plus 1/2 times negative 9.81 times 18.35 squared. All right, so and I'm rounding here, guys, just because I'm lazy. Okay, plus 0.5 times negative 9.81 times 18.35 squared. Whoop. I didn't half the time. You're exactly right on that. Yep. Okay, so entry. That'll work. That's better. 412. Okay. And the reason it came out to such a small number is because the way I did it, it should have actually come out to 0. But because I rounded off, I still got a tiny little fraction of a number, right? But if I use the actual full time, I should get that my vertical displacement is 0 because I come back down to the same elevation I started from. Okay. Okay, that's why you have to half the time. So getting 412 meters that way. The other way, okay, is to do it like this. D equals VF squared minus VI squared over 2A. So we're looking at 0 squared minus 89.99 squared divided by 19.62. Okay, we should get a similar number there. So 89.99 squared. All right, pretty much the same number, 412.7522. Okay, again, that's because I rounded off and didn't use the full number. Okay, if I'd used the full number, I would have got exactly the same answer both ways. Okay, everybody all right with that? Okay. I think that one was like 3 semesters ago or something like that I used that on the unit exam. So you get a pretty good idea of the kind of thing I typically ask, okay, in regards to projectile motion.
You don't have to give us the numbers, but like, what's the scenario going to be for this test? Is it going to be like a car, a cannonball?
Oh, I don't know. I haven't decided yet.
Can it be something really cool? I focus better when it's
Okay, I'll try and make it cool. I'll put a picture and everything.
a dinosaur doing an ollie on a skateboard, and then we have to measure like his arc. Yeah, and we get an extra mark in color.
It'll already be in color. I always print the exams in color.
But like leave it white, and then we have to color it.
You're not going to have time for that. No, you're not going to have, yeah, something to do would be the test. Yeah. No, the test is unfortunately not just that one question. Okay, here's a tricky one. Okay, this one's a bit trickier because we haven't done one. This one's looking for the angle at which you throw the projectile. All right, so it gives you way different information. This time it's giving you how long it's in the air for. Remember I said that that's pretty rare? Okay, here it is. So it's in the air for 2.5 seconds. It lands 70 meters horizontally from the point it was thrown. Same elevation. Okay, same elevation. That's the key here. All right, and it's thrown into the air at a velocity of 35 meters per second at that unknown angle. All right, so the start of this is like this. This is 35 meters per second. The angle is unknown. Okay, we're looking for the angle. We still know that this is going to apply. It's going to travel in an arc. Okay, it's going to do all that other stuff. But this time we actually know it's in the air for 2.5 seconds. Okay, we also know that the acceleration is negative 9.81 meters per second squared. That's not changing. And we know the horizontal distance. It's 70 meters. Believe it or not, this question is very quick.
Yeah, it looks like it could be.
Okay. All right, I'll give you a minute or two on that one. Okay. I wrote the time over here just to throw you off. This time can also be used over there. What will it help me calculate? The horizontal velocity, which would give me a second side for this triangle. Once I have two sides, can I get the angle? Okay, so that's all you have to do. Okay, you calculate V by going 70 over 2.5, and then you do trig to get the angle. Okay, like I say, once you realize that's all you had to do, it was quick. It was two quick calculations. All right, tomorrow you will have a quiz. It will have projectile motion on it. I will post it later.
Stuff or just horizontal?
Both.